Good morning, everyone.
Yes,
I think it's time to start the session. The first speaker is Professor Massimo Della Valle, who will speak about supernova and gamma ray burst connection. I have 25 minutes and I will tell you a couple of several minutes before.
Okay, thank you so much. First of all, thanks to good afternoon and good morning to everybody. And thanks to the organizer to give me the chance to attend this exciting meeting. In my talk, I will try to touch different aspects of supernovae. So basically, give an overview of the current supernova taxonomy. Then I will describe the properties of gamma ray burst supernova in terms of progenitor mass and size. We'll expand the issue of gamma ray burst and supernova rates. And then I don't have a conclusion, but well, I should have someone, but more than conclusion are open issues and perspectives. First of all, why to study supernovae? Because supernovae affect most of the research field of modern astrophysics. Just here there is I make some example. So physics of the explosion of supernovae is connected with the physics of compact objects, with the chemical evolution of the host galaxies. With cosmology, we learn by studying Taiwanese supernovae at cosmological distances that the expansion of the universe is accelerated. Then we can use the high redshift object has like supernova or gamma ray burst. The redshift of the order of up to 10, and to use those objects as the cosmic beacon to study the intergalactic medium and to explore the so-called reionization epoch. Then there is the connection between supernova remnant and cosmic rays. And finally, in 1987, with the discovering of neutrinos from supernova 87A, we opened the so-called multi-messenger era. What supernova? Well, okay, supernova was a recent term in astrophysics introduced by Valle and Izzo in 1934, but they also they did something really very. They did much more than that. They made the prediction that I just report here from the original paper. With all reserve, we advanced the view that a supernova represents the transition of an ordinary star into a neutron star consisting mainly of neutrons. Such a star may possess a very small radius and extremely high density. And thanks to the observation of Chinese astronomers that were mentioned by Professor Ruffini this morning, we were able to track back and to observe the supernova remnant of the famous Crab Nebula. The supernova exploded in 1054, and with a multi-wavelength approach, now we were able to confirm the original idea and prediction of Valle and Izzo by observing the pulsar associated with the Crab Nebula. Before the term supernova, these stars that suddenly appear in the sky were labeled gas stars. But you immediately understand that looking at this dozen of objects that occurred in about 2,000 years, that is almost impossible to study supernovae just waiting the next galactic supernova. And this is well summarized, this concept, by looking at the current supernova rates. Look only to the pink box, and you see that we have one object. We expect to observe one object every centuries, more or less. The only way to increase this number to increase the observable number of supernovae is to increase the volume that we can sample with our telescope. And this was the duty that was started in the 50 by Zwicky. And with this relatively small telescope, he started to discover about between 20 and 30 supernovae per year. On the basis of this sample of supernovae, it was possible to go through the first supernova taxonomy. And basically, all supernovae can be, at those times, divided in two classes, type 1 and type 2. Type 1 are characterized by the lack of hydrogen in the spectra and this prominent absorption that you see at 6,155 angstrom due to silicon-2. Type 2 supernovae were characterized by the massive presence of hydrogen. And basically, according to the original paper by Minkowski, the so-called type 1 supernovae form an extremely homogeneous group, while the other type 2 they present individual differences. And this is, and this homogeneity and dishomogeneity in the spectra is well reproduced in the photometric behavior. At the up left, you see the average light curve of 40 type 1 supernovae, and you see that they have a little scatter at maximum light of the order of 0.3 magnitude. While type 2 supernovae, bottom right, you see a range of magnitude of the order of 6 magnitude that in terms of luminosity imply a factor 250. The important point is the following: that the type 2 have never been observed in elliptical galaxies, but only in irregular end spirals, where the star forming is still active. And type 1 occur in all type of galaxy, star forming and very old passive ellipticals. So if we consider that a massive, the more massive is a star, the shorter is the lifetime on the main sequence, and this relation goes as the mass to minus 2.5. That implies, for example, that the sun that spent 10 billions of years on the main sequence, well, for a star that is 10 times more massive, this lifetime corresponds to 30 mega years. And so these simple observations of the place where the supernova occur lead to the idea that their progenitors are massive when the collapse of the core occurs. What about Taiwan that we see now, we call Taiwanese in the modern classification? Well, they come from the disruption of a carbon-oxygen white dwarf in a binary system. Doesn't matter if, doesn't matter. It is still a matter of question if the binary system is formed by two white dwarfs or by a white dwarf which accretes material from an evolved low mass secondary companion. An important step will occur in February 23, 1987, when a supernova exploded in the Large Magellanic Cloud. And the budget associated with this kind of explosion is of the order of 10 to the 53 ergs, and 99% of this is emitted as neutrinos. And if you can see, if you make a rough computation, you can estimate that 9887A supernova emitted about 10 to the 58 neutrinos. Well, only 25 of them were detected, but that was enough to confirm the late stages of stellar evolution. In other words, that a neutron star was the residual of a core collapse supernova. I spent 4 years of my life in Chile trying to observe this neutron star. Unfortunately, we didn't discover yet. Anyway, let's go on. The explosion of 87A supernova had three important consequences. A number of surveys to search for supernovas started, also with a relatively large telescope. And so, as you see here, from 87A, this boost of interest implied that from a few dozen of supernovae per year, we in the early 2000s, we start to discover almost one supernova per day. And this has as a consequence that we can refine the supernova taxonomy. And today is much more complex than before, than the previous slides that reported in the previous slides. I cannot go into the details because this requires, a lot of time, but still we can have an important hint from the place of occurrence of these supernovae. Again, only Taiwanese supernovae occur in all galaxies, while type 2, 1b, and 1c only in star-forming galaxies. And this allows us to still keep this division in two families. The Taiwan now become Taiwanese, so they're thermonuclear. They come from the disruption of the carbon-oxygen white dwarfs. And all the others, they come from the gravitational collapse of the core. So they are massive stars, basically. The other important consequence was the discovery of Taiwanese supernovae at very large distances. And this has allowed to discover the acceleration of the universe. The other important point was basically in the same years when a number of satellites observing the sky at high energy started to clarify, to identify the origin of the mysterious gamma ray burst that was discovered about 30 years before. This, I think that this will be the talk by Luca, so I will skip it. This flash of gamma rays. But what is important that there are basically two families, and one of them, the so-called long gamma ray bursts, are associated with hypernovae. And the first case of association was discovered in 1998 when gamma ray burst 980425 was associated with this supernova. And what are okay, gamma ray burst supernovae have many important properties, but probably the most two important are the following. First of all, the lack of hydrogen and helium in the ejecta. That means that when the progenitor explodes, the huge envelope of hydrogen has been already lost for secular evolution, and so they are really massive stars. And the spectroscopic features, and you see if you compare with the right side, that it is let's say a standard core collapse or type U supernova, you see on the left side very, very broad expansion velocities that can be, and you can measure that with simple spectroscopic observation, taking advantage of Doppler effect, and you see 30,000 kilometers per second. And so these hypernovae or gamma ray burst supernovae can be associated, are a subclass of this 1C, 1BC supernovae. So they are massive stars. So they are, as you see, very energetic event. 98 BW was an order of magnitude more energetic in terms of kinetic energy of the ejecta than 87A. And what about the progenitor mass? Okay, I don't go into that. Okay, I can do that here. Look, for example, type 2 supernovae. You see the 50% of type 2 supernovae in Y, you have a fraction of objects, and in X axis, you have the fraction of light of the supernova, of the host galaxy. So look at the blue track. The 50% of type 2 supernovae basically correspond to almost the 50% of the light of the host galaxies. And this is quite reasonable. Now look at the gamma, long duration gamma ray burst, the black stuff, the black line. 50% of them occur in the 90% of the light of the host galaxies. And this implies that long duration gamma ray burst erupt in the brightest region of their host. So basically their lifetime is so short that they have no time to drift apart from the place where they were born. And so basically they die and, they born and die in the same place as happened to many of us, by the way. So from an analysis that no time to explain, we were able with Cody-Raskin to derive the mass of the progenitors between of this long duration gamma ray burst in between 30 and 50 solar masses. What about the size? This is a typical size of a progenitor of type 2 supernova, red supergiant. This was the size of the progenitor of 87A, a blue supergiant, 10 to the 12 centimeters, so an order of magnitude smaller. And the progenitor of a long duration gamma ray burst are pretty small, a Volta-Rayet star with a radius that is of the order of 4 times 10 to 11 centimeters. So much, much smaller. What is the rate of gamma ray burst? Well, this is a pretty small number, not larger than 1.5% of all family of, when we compare with the whole family of Taiwan BC supernovae. And when you consider that 1 BC supernovae are only 30% of the family of core collapse, you find a rate between gamma ray burst and core collapse is of the order of 10 to minus 3, which correspond to have one event every 100,000, every million of years in a galaxy as the Milky Way. So they are very rare phenomena. On the other hand, if we compare the ratio between the progenitors, well, this ratio should be much larger, of the order of 50%, by assuming a salpeter IMF. And so the question is, what causes some small fraction of core collapse supernovae to produce observable gamma ray burst, while the majority do not? Okay, this is, if you want, is a conclusion, but is the open issues. And so we should, what we are doing today is to study, to try to analyze, to study these special requirements for a massive star to become a gamma ray burst. And here I have list a number of them. In particular, I want to stress the binarity that is neglected in almost in most of the models, with the remarkable exception of the so-called induced gravitational collapse that has been elaborated in ICRANet by Remo Ruffini, Gueda, and many others. I think also Luca has been involved in this. High rotation is extremely important. Asymmetric explosion. Okay, I'm sorry, but I don't have to go to all of this. Finally, my last 3-4 slides are about the perspectives. In these last years, an incredible number of surveys started to discover transient and to study supernovae, of course. And now today we are, I keep the previous plot on, so I put on the same scale, and today we are discovering 1,000 supernovae per year, so basically 3 per day. But what is going on, what will happen in a couple of years from now will be dramatically exciting. With the Vera Rubin Observatory and also the former LSST telescope, 8-meter class telescope devoted to surveys. Well, this will discover about 1,000 supernovae per day. So look at the plot is the same that I showed you before, but now is not supernova per year, but is supernova per day. And so finally, what is the role that can have a 4-meter class telescope as your telescope, your beautiful telescope, in the era of 8-10-meter class instruments? Well, I was to try to answer to this question. As you see, the question is relatively easy, but the answer is not. I was looking at the telescope productivity, and here I was going through the papers that have been produced by telescopes, by 8-10-meter class telescope plus 4-meter class telescope in between 2005 and 2020. And you see that, for example, NTT, that was the first 4-meter class telescope equipped with an active optics, is still doing an excellent work. Compared, his productivity in terms of papers is comparable to the Magellan or the Stewart Observatory. They are 6.5-meter telescope. In terms of highlights, that means only I consider only the paper on nature and science. Of course, in this case, HST is the Hubble Space Telescope is making most of the job. But still, NTT and TNG have a productivity that is compatible with with even larger telescope. And what is the key to keep a 4-meter class telescope competitive in the era of 10-meter class telescope? Or in my opinion, is to specialize it. For example, NTT will work only with one instrument, SOX, for example, that will start in 2003 at the European Southern Observatory in La Silla, at the Observatory of La Silla, not a Paranal, where there is the very large telescope. And this instrument will be devoted to study, all the transient, all the science cases related to the transient in the sky. And the other example that I want to take is our telescope, Italian telescope, at the Canary, the Galileo Telescope. That now basically most of its time is used to the search of exoplanets, and this allow to this relatively small telescope to keep a rate of breakthrough that is of the order of basically one per year. That is not so bad. Okay, I have finished here. I hope to be to match my time. Thank you.
Massimo, yes, you were perfect on time.
Great. Thank you, Carlo.
And so we have time for some questions.
Can I ask a question, please? Yes, so this is Habib again from the National Observatory Project. Well, thanks for the last few slides for putting this in the prospect of the Iranian National Observatory Project. We fully agree with you. The only thing that we are trying to also do at the same time is to build the community. Therefore, we want to be as basically as general as we can be to incorporate and include as many astronomers as possible within the country and the region in our project. So, but going back to your scientific part of your presentation, for technical reason, I missed one or two slides. What fraction of the GRBs are in fact supernovae?
Okay. I think this could be the slide that you miss. Okay, this the ratio between long duration gamma ray burst and type 1 BC supernovae is in between 0.02% and 1.5%, and this range is related to the so-called, let's call beaming factor. 1.5% correspond to a beaming factor of the order of few degrees, and 0.02 correspond to the case of isotropic emission. Is it that your point?
Yes, I remember back around like 2000, there was a paper at that time. I remember there was something called like the SGRBs, and SGRBs from BPOSAX or others were recognized to be covering about 10% of the GRBs. Like, is the SGRBs are the same as like supernova GRBs?
I think maybe you refer to the low luminosity gamma ray burst, but look, your number about 5-10% remind me the ratio between the hypernovae and the gamma ray, long duration gamma ray burst, because there are hypernovae that apparently are not related, are not associated with gamma ray burst. Maybe they are beam and we miss, and our satellite beam miss the observation of the high energy component, and so we see only the say, let's call the 4 pi emission. So the supernova. Well, sorry, I should be more. I should expand this point, and I have also the slides prepared, but I need to talk about 2 hours, so I can't.
Yeah, I appreciate that. Thank you very much. Thanks a lot. I enjoyed it.
Thank you to you. Thank you for the question.
Thanks, Massimo. Other questions or comments? So if not, let's thanks Massimo again. And
yes, I fully agree that we have to keep going on this point with a dedicated workshop with Massimo and everybody else, because now we are gaining much more understanding even about the different gamma ray bursts participating with the supernova connection. It's clear that there are 3 different kinds of gamma ray bursts which are associated with supernova, and we are very close to understand the physics of this process. Therefore, we have to reconvene soon on a discussion on this matter, and maybe the next meeting of ICRANet celebrating the 50th anniversary in Colombia could be a good occasion to focus on this specific point, because we are really doing daily progress. Remrufini.
Yes, I also agree with this point. Okay, so thanks Massimo again, and let's move on the next speaker, Professor Luca. So, yes, you can see you, Luca. And can you share the screen?
Hello, everyone. Okay, do you see my slides?
Yes, we see them very well. Gamma ray burst in the
Hello?
optical.
Okay, I'm not sure that if you can hear me because the connection is not very good. Carlo, can you confirm that you can hear me?
I can hear you well. The video is a bit shaky. I mean, it's not fluid. But,
Yeah, because
the audio
working from home is not the best in this time. And yeah, I think that we can move on. And but before starting my talk, I would like to thank you, the organizer, for giving me the opportunity to present some slides about gamma ray burst in the optical domain. Unfortunately, well, I would really love to attend this meeting in person and visit your beautiful country. I hope that there will be in the future more opportunities to doing this. So my talk is related on the observational side, particularly in the optical domain of gamma ray burst. I've seen that in the program, the program of this meeting, there will be several talks about theoretical interpretation of GRB emissions. So I was thinking that maybe an introduction, phenomenological introduction to this very energetic event was needed. So what are gamma ray bursts? As you can see in this small PNG file, they are bright flashes of very high energy radiation emitted in gamma ray in the keV MeV energy range, and their emission in the gamma ray is very heterogeneous, with the light curve duration that can vary from a fraction of a second up to a few minutes, sorry. The spectrum emitted by these events, so for spectrum we mean the distribution of the photons in the gamma ray energy range, is mainly non-thermal emission, which jointly to the millisecond variation of the light curve suggests a superluminary motion, a high relativistic emitter source as progenitor of these events, and integrating their observed flux along the entire duration of the prompt of the gamma ray emission, and considering the observational evidence that GRB are cosmological sources, the total energy emitted in these short events is comparable to almost a fraction of a solar mass, which is a huge energy emitted in a few seconds that can be only explained with the formation, with a catastrophic event leading to the formation of a black hole. So in this plot, you can see just a morphology, different morphology of how gamma ray bursts appear to a gamma ray detector. This is a famous image obtained with the BATSI in the early 90s, the BATSI detector on board the Compton gamma ray observer instruments. And you can see that the GRB are not similar, there are no two similar GRBs. So we can have very short duration GRBs with a duration of a fraction of a second, or fast ride with an exponential decay pulses, or also complex emission characterized by multiple spikes. And in some cases, we have also some precursor anticipating a main emission event. In some cases, we also have short GRB, very spiky emission, followed by an extended softer emission. The spectrum is, as I mentioned before, is non-thermal and is well described by a phenomenological function that was named the band model. This This function is just a model that in its origin comes from the technique used to analyze X-ray data. So, the spectrum is mainly well described by two power laws mutually connected at a given energy in the gamma rays, which is also called the peak energy, and characterize the hardness of gamma ray bursts. Indeed, GRBs can be divided as we got more and more data with time from these events. One of the first evidences was that gamma ray bursts can be divided into classes, namely short and long, based on the duration of the prompt gamma ray emission, where the dividing line is the time interval of 2 seconds. However, this classification is not only apparent from the light curve, but it's also mirrored in the spectrum of GRB. So we have that short events, so GRB lasting less than 2 seconds, are also harder events. So with a peak energy, with a spectrum which is more clustering at high energy frequency. And this evidence led to the proposal that these two different families, so GRBs, come from two different progenitors. So with long gamma ray bursts originating from the collapse of a very massive star, whose collapse leads to the formation of a black hole, and the same happens for short gamma ray bursts, that they originate from the merging of two compact objects, namely two neutron stars or also two black holes. And when we have the formation of the central, the newly formed black hole, it can accrete matter collapsing into the black hole itself, emitting a collimated emission that gives rise to the gamma ray. And then as the jets start to interact with the external medium, it also emits a synchrotron emission giving rise to the afterglow. Indeed, well, okay, I have just, after the talk of Massimo, I have included this text mentioning that, following the comment made before, that long GRBs are connected to supernovae and short GRBs are connected with compact objects. Just a few months ago, it was published 3 papers about the first evidence of a short gamma ray burst connected with a supernova, but I'm not going to talk about this. So after that, when the relativistic emission starts to interact with the external medium, the circumburst medium, we have the forward shock propagating in this medium, leading to the afterglow emission. And this emission is not similar to the prompt; it's more homogeneous and can be characterized by 3 families. With mainly, we can have a simple power law decay for the more energetic GRBs, or 3 power law, the classical canonical emission, with the first decay emitted from the high latitude emission from the prompt, and followed by a plateau and a late decay for the X-ray afterglow. So GRBs actually are not only high energy events. So far we talked about emission observed in gamma rays, but really as the emission goes on, the synchrotron peak moves to longer wavelengths, so that GRBs can also be observed at optical range as well as in the radio, in particular, as longer as is the wavelength of the emission from GRBs, the time scale is much longer. So in the radio, we can observe GRBs up to hundreds of days from the emission of these events. And what is really interesting is that optical and radio frequencies are 2 electromagnetic windows that can be explored from ground telescopes, while gamma rays and X-ray, we only need satellites. So in particular, now I will focus mainly on the optical range, given that radio and gamma rays and X-rays will deserve a dedicated discussion. So the first results obtained when GRBs were observed in the optical was that they are cosmological sources. So in the late 90s, when the first afterglow was detected by Beppo Sachs, and the first optical afterglow was detected immediately after the detection of the X-ray emission, it was discovered that GRBs are at cosmological distances, in particular thanks to the observation in their optical spectrum of absorption lines originating in the immediate in the immediate surrounding of the GRB itself. In the case of 990705, GRB at redshift, if I remember correctly, 1.2. The redshift was determined by the identification of absorption line of magnesium and iron 2, also fine structure of iron 2 elements. But in the last 20 years, we have obtained a lot of spectra from GRBs, and actually, we also measured the most distant GRB known so far, the 90429b, that was observed at the incredible redshift of 9.2, so actually almost 500 million years after the Big Bang. This means that gamma ray bursts are very powerful probes for the study of the reionization era, when the first galaxies and stars formed and started to reionize the universe. Indeed, from the analysis of gamma ray burst spectra, we can obtain a lot of information related with the properties of the surrounding, of the medium of their host galaxy and their immediate environment. For example, from the identification of their absorption line, we can measure the abundance of the gas, including molecules. In particular, in this case, we a paper from Casper Heinz et al. It was identified molecular hydrogen in the spectrum of gamma ray bursts. At the same time, given that, as Massimo mentioned in his talk, GRBs almost die in the same region where they born, the observational rate of gamma ray bursts is a good trace of the star formation rate. So they are very good indicators for the evolution of the star formation at high redshift, where we do not have many probes. Another important use of GRB at high redshift is that from the modeling of the UV rest frame UV emission, it's possible also to estimate the amount of ionizing Lyman alpha photons that escape from the from the environment of GRB. This is important in order to understand what is the role of the first stars and galaxies into the reionization of the universe. And we also, and as we will see in the later talk by Lorenzo Amati, GRBs can also be introduced as distance indicator, given that there are some photometric and spectroscopical correlation between observable of GRBs, but I won't focus on this topic. So now, the one from the optical point of view, if we want to observe GRBs at high redshift, actually we need telescope and detectors that are capable to observe at a longer wavelength as possible. In particular, if we want to arrive at breaking GRBs at redshift larger than 6, we really need detector in the near infrared, given that the Lyman alpha true at this redshift is around 10,000 micron when almost in the near infrared range. In this case, the first GRB for which the redshift was determined first photometrically, 50904. It is clear. It is shown here in the left. Unfortunately, I didn't put the label, but in the left image, this is an image obtained in the J band, while this image, where there is no detection of the GRB, was obtained in the Z band. This suggests that we have the break of the Lyman alpha between these two bands, corresponding to break. Well, this is in frequencies, but corresponding to the redshift of the position of the Lyman alpha at 6.4. From the optical, in the case of nearby GRBs, generally nearby GRBs are much more brighter than cosmological events, so it is possible to follow up them up to dozen, if not 100 days from their discovery. And in a few cases, in very nearby cases, it was discovered the emerging of a second component around 10 days from the GRB explosion, which was determined to be the supernova associated with gamma ray bursts. Like Massimo already discussed this aspect of GRB, and I'm not going to focus more on this side. I would like to concentrate mainly on something more practical, like, for example, what we generally do when we have a detection of gamma ray bursts, and how we can react in real time to get the most important, most precious information from them, given that they decay very quickly. So once a GRB is detected by a constellation of satellites, there is a transmission system that was initially built in the 90s for the BATS, the Compton gamma ray detector. It's still working very efficiently with great success. So when we have a first detection of gamma ray burst by satellite like SWIFT, Fermi, Integral, or other GRBs, this detector immediately transmit a quick position for the gamma ray detection field of view. And it's transmitted to a radio antenna on ground. And this transmission is directly broadcasted worldwide through two systems. One is an virtual observatory XML protocol, but another system is through the gamma ray circular network. The gamma ray circular network is public. Anyone can access this set of circular, and the information on the real-time detection of GRBs and not only, also further data from X-ray and optical telescope is transmitted through this network to optical telescope and also multi-wavelength detectors such as radio and TV telescope working on ground. And in my case, sorry, someone has a question? Okay, it was only noise. So I work mainly on a couple of collaborations using some of the biggest telescopes on ground dedicated to the observation of the optical counterpart of gamma ray bursts, in particular the spectra. And we use some of the largest telescopes on ground, such as the Gran Tecan, 10-meter telescope in La Palma, the VLT in Chile, but also a very efficient telescope, which is a 2.6 meter, not very big telescope, still in La Palma, which is the Nordic Optical Telescope with the Alphosk instrument, which is very efficient in observing GRBs and getting spectra. So let's see what happens when we have some interesting source. So the first information we get is from GCN Circular. And this is an example of an event exploded 4 years ago, on the 5th of April, was a GRB with an optical counterpart reported by the U-boat detector on board SWIFT. And when we have a detection by U-boat, in this case with an estimated magnitude of 16 in the white filter, this is an image that can be easily obtained from the SWIFT XR2 Lesser website. Is a public website, public resource that anyone can access to. We were, well, as we all see this information from some interesting GRB, we immediately trigger big telescope if the GRB is visible from the different location from the Earth. And in this case, we triggered the Gran Tecan and obtain a spectrum of this event about 7 hours from the GRB. And this is well, the most important slice of the Gran Tecan spectrum, showing the Lemma true at redshift 3.5, redshift that was confirmed also by the presence of other transition of high ionization elements such as silicon-4, carbon-2, and ferromagnetic also oxygen at the same redshift. So yes, this is the text showing the identification. But for more nearby event, which is this is my main topic. For very nearby events that are not so many in the case of GRBs, the interest is much higher because we can not only determine the redshift or study the immediate environment, but also try to detect a rising supernova. So in the case of 1712-05, the third GRB closest to the Earth, this GRB was detected the 5th of December 2017 at 7:20 UT, and we immediately situated GCN because we have found a bright spiral galaxy coincident with the position transmitted by the Swift detector. And we submitted the circular almost 1 hour after the GRB detection. So well, immediately after the GRB detection, I personally triggered the VLT telescope, and we got the confirmation of the redshift of this gamma ray burst, which was very close at about 150 megaparsec. But the most important thing is that we continue to follow up this GRB because it was very bright, and we 2 days after the detection by Swift, we reported in the spectrum some broad undulating spectral features that resemble the rising emerging of a supernova emission. Indeed, this is a spectral series for these events. The bottom spectrum corresponds to the first observation from at the VLT, showing a classical Pavlov behavior typical of afterglow-dominated emission. But already from day 1 and day 2, the emergence of undulating features that are the black curve, the red curve are spectral simulation. Don't pay much attention to the red curves. The black curves already were showing around 4,000 and 6,000 angstrom, typical features observed from emerging from supernova 1C borderline associated with gamma ray burst. But not only, but the spectral observation are not the main source of information for gamma ray burst. In particular, with just 1-2 meter plus telescope, it is possible to get very precious information from GRBs. The most important constraint is that which telescope should start to observe very soon a GRB from the detection of the same energy event. For the case of 171205, for example, we started a campaign, multi-filter campaign with different telescopes, and you can see that within 1 day, we have obtained different multi-bands observation of the afterglow of these events that led to the, when we joined the optical and near-infrared observation with the X-ray data from Swift, we realized that there was an extra component associated with this gamma ray burst that was interpreted as the cocoon emitted from GRB supernova. But the most important message is that it is still very important, despite we are observing GRB from more than 20 years, to obtain very quick observation, particularly multi-filter observation of GRBs few hours after their detection in order to get important results, important constraints on their emission. Just a word about short gamma ray bursts, because the same reasoning applies to these events. Short gamma ray bursts are associated with the merging of compact objects, and we know from the famous 2017 event that was associated with the gravitational wave event of 1708-78, that the associated optical emission, optical near-infrared emission, became very quickly, and the accompanying multi-filter optical follow-up reported the presence of a black body component that was later interpreted as the emerging kilonova, where spectral obtained from VLT and other facilities led also to the possible identification of arc process element. But what is the main message from the optical side is that from the optical modeling of the evolution of these events, since kilonovae are not spherical, simply spherical emitted, but we have two components, one bipolar and another one toroidal, we can infer the inclination angle of the binary system from the optical observation, and constraining the modeling infer from the gravitational wave analysis. And in this case, in the paper by Suhail Dhawan, it is possible also to improve the constraint on the Hubble constant, also from a single observation event. This is the best example to show how multi-filter optical observation are very useful, also for single events. Few last slides, few minutes, just mentioning another important application of optical observation of gamma ray bursts. So we know that GRBs are observed in the brightest region of their host galaxies, because they are the progenitor of gamma ray bursts are very massive stars with an average life of a few mega years. So generally, they explode in the same region where they form, that are massive H2 region, and H2 region are the brightest. Some of the brightest region in the host galaxy, since we have the formation of stars. And with the use of new advanced detectors, such as integral field unit, that are, briefly speaking, in a few words, I'll try to explain this kind of detector. So imagine that you have a fiber or a microlens at each single pixel of an astronomical image. This fiber is, or microlens or lens array, is indeed connected to a disperser element, providing a spectrum for each single pixel, which in this case is called spaxel, covering the entire field of view of your telescope. In this case, as a final result, you do not have a two-dimensional image, but you have a three-dimensional data cube, where the first two dimensions correspond to the typical spatial right ascension and declination, and the third dimension is the wavelength. So in this case, you can spatially resolve the astronomical source that you are observing. And for the case of nearby gamma GRB host galaxies, it's also possible to provide spatially resolved maps. For example, in this case, we were capable to study the metallicity, the gas metallicity from the M2 index. The M2 index is a ratio between two emission lines. The light cross corresponds to GRB position and is indeed located at the region with the lowest metallicity in the galaxy. But also, we can study the star formation rate and also the velocity, radial velocity maps of the galaxy. So this is another almost pioneering field, since there are few few GRB host galaxies published in literature, and now also with the launch of JWST telescope that will mount the NIRSPEC detector that is an FU in the near infrared range, we can really start to do this kind of science for GRB host galaxies. Okay, last few words about the host galaxy of the kilonova event. With IFU, you can also study the stellar population, not only the gas component. And for stellar population, you need stellar synthesis population codes such as Starlight, Optical, FX, or PPAS. And from the modeling of the final result, you can study the star formation history of each host galaxy of GRBs. And in this case of the kilonova event, we had the confirmation that the host galaxy is mainly composed of old stellar population, as it is expected for early tech galaxies. So I think that I am on time. This is my conclusion. Then I want to go through all the bullets, but just want to mention that optical observation of gamma ray bars are still very crucial and represent an important source of information, not only for the modeling of the GRB stream itself, but also for the study of the environment where the stellar population originating their progenitor. Thank you very much for the attention.
Thank you, Luca, very much. And we have time for some questions or comments, please.
Can I ask a question, please?
Go on.
Yes. Oh, hi, Luca. Thank you very much. This is Habib from National Observatory again. You mentioned about the time difference between the detection or reporting the SWIFT, for example, alert, until we are capable of actually doing this spectroscopy of the GRB. I understand that one tricky part is that SWIFT, for example, would report the position of the source within some 1 or 2 minutes or up to 4 minutes accuracy. And obviously pointing at a telescope, especially if it's a large telescope, which generally have a small field of view towards that, is cumbersome. You need some more accurate the positioning of the source in order to be able to do a spectroscopy. but what is the record spectroscopic measurement of GRBs? Is it still, like you mentioned, like 7 hours? But
do you mean in terms of? Oh, sorry.
Yeah. So I'm trying to understand how quickly people have managed so far to do a spectroscopy of GRBs.
Look, for the GRB that I mentioned, probably is one of the most early spectrum that we have obtained. We managed to get a spectrum 1.5 hours after the GRB detection. But this was a special case because I can tell you that as the GRB was detected by Swift, I called the VLT telescope. So I had a direct phone call with the operator. So it was just not an automatic reaction, it was a human reaction to this event. But there are other telescopes that mount some rapid response mode that can react in real time automatically to GRB detection. But the order of magnitude of time is this one few hours after the GRB explosion for spectroscopy. But while for photometry is much more quick, there are surveys such as MASTER, which reacts few seconds after the GRB detection.
All right. Okay. Well, thank you very much.
And I have one or two questions. Can you hear me?
We hear you very well.
Yes.
Sorry. Okay. Hi, Luca. Sorry. Thank you for your interesting presentation. I have two questions. One of which is related to the progenitors of the GRBs, and the other is to the physics behind the justification of jets in GRB phenomena. Thank you.
Yeah, go ahead. Hello?
Hello. Sorry, Luca. Did you hear my questions?
Can you, sorry, I have a problem with Carlo. Can you repeat your question, please?
Okay, sure. I have two questions. One of them is related to the progenitors of the GRBs, and I mean the sources of GRBs. And the other one is to the physics behind the justification of jets in this phenomenon. Thank you.
So, do you want? I don't understand.
Yeah. What are the sources of the GRBs? Where are they? Yeah.
So, if I answer to your question, you are wondering, well, what is the relation between the progenitor and the emission? So, but actually, there are the central engine that. Well, let's say the intermediate step from the collapse of the supernova and the jet formation is still something that is not clear very well. Well, there are models for which we know very well what is the central engine, what is the physical mechanism giving rise to the jet. But in general, we have accretion onto a new form black hole. In some cases, some people also propose a magnetar model. And the black hole is capable to produce this collimated emission, giving rise to the observed phenomenology. Gamma rays originate from internal shocks, while as the jets start to interact with the circumstellar medium, take into account that GRB explode in H2 regions that are very dense regions. So as a jet starts to the jet is located in a very dense region, and as it starts to interact with the combust medium, we have the formation of a shock emission, forward shock emitting synchrotron due to the presence of magnetic field internal.
Okay, but the origin of the GRBs.
Because there are
the origin of the GRBs. Sorry, where they come from? The GRBs.
The origin.
Well,
the gamma ray emission.
No, the progenitor. This was mentioned already by Della Valle, about the binary system. And we will come back in the next days about detailed results about the binary creating the GRB of different family. And also, but this is a theoretical work, and Luca was mainly looking at the data observation. And you are asking about the theory. The theory will be addressed by 2 or 3 lectures, including one of Gueda and Yangli, and about the mechanism of the emission of the JEV, which is a very, very specific. Fortunately, we have some model which we will present also in the next days by Rahim Moradi.
Thank you so much, Prof. Profini.
Are there other questions?
So, can you hear me, Luca?
Yes, we hear you, Soroush.
Yes, Soroush, go ahead.
Okay, just I want to take this opportunity to sincerely thank you, because I know you were in a hard moment and you accept our invitation. And actually, we have heard the beautiful voice of your new baby, and we congratulate you about that. And thank you so much for accepting our invitation. That was amazing talk.
Congratulations from
Thanks
all
a
of
lot,
us.
Soroush. I really appreciate. Probably you were hearing the baby screaming
Yes,
while
that-
I was
yes.
talking. I'm not sure.
What is
yeah,
the
we are-
name?
Okay,
What is
thanks
the
a lot
name?
for.
What is the name you gave to your son?
Name is a daughter. The name is Lea.
Leah.
Lea.
Okay, the first time that she's presented worldwide. Congratulations again.
Okay. Thank you so
Thanks
much.
a lot, everyone.
Thanks.
So, I think, Carlo, we can stop here, and then the next session will be started around one hour and a half.
Yes, in 1 hour and a half, we'll start again.
Yes,
Okay.
yes. Actually, in 3:30 in Iranian time, and we start at 1 p.m. in Italian time, or CET, let's say. So,
Yes.
Okay.
Okay.
okay. Thank you all the speaker of the morning session.
Good.